There is a phrase that keeps appearing in scientific papers, published by astronomers using the James Webb Space Telescope. It keeps showing up in peer-reviewed journals, in official NASA statements, in the carefully worded language of researchers who spent their careers building models of how the universe works. The phrase is this: we did not expect this. Not once, not twice. Dozens of times. Across dozens of discoveries, from some of the most respected institutions in the world, the conclusion keeps coming back the same way. What James Webb is finding should not be there. The galaxies it is seeing in the earliest moments of the universe are too big, too bright, too structured, too chemically complex for our models to account for. The planets it is finding have atmospheres that physics says cannot survive. The objects it is detecting do not fit any category science previously had a name for, and the researchers responsible for interpreting this data have now begun using language that would have been unthinkable in cosmology just 5 years ago. One study author said publicly, and this is a direct quote from a published paper, that there is a growing chasm between theory and observation related to the early universe. Not a small discrepancy, not a minor calibration issue, a growing chasm, meaning the gap between what we predicted and what we are actually seeing is getting wider, not smaller. The more data we collect, stay with me, because what James Webb has found in the last 3 years of operation is not just a collection of interesting space discoveries. It is a systematic challenge to the framework that scientists use to understand everything. Start with a discovery that has shaken cosmology more than any other single finding in recent memory. When astronomers first designed James Webb's observational program for the early universe, they expected to find galaxies from the cosmic dawn period, the first few 100 million years after the Big Bang, in a specific condition: small, chaotic, irregular, chemically simple, because the heavy elements that more complex chemistry requires had not yet had time to be forged in stellar furnaces and distributed across space. This was not a guess. This was a prediction derived from decades of theoretical work, from simulations run on the world's most powerful computers, from the accumulated understanding of how gravity, gas, and time build structure from the near-uniform soup of matter that the Big Bang left behind. It was the consensus, and James Webb began systematically contradicting it almost immediately. The finding that crystallized this problem most sharply is a galaxy designated MOMSI-14, identified in data from April of 2025 and published in early 2026. MOMSI-14 existed just 280 million years after the Big Bang. To put that number in context, the universe is approximately 13.8 billion years old, meaning this galaxy formed when the universe was roughly 2% of its current age. Under the standard model of cosmology, a galaxy at this cosmic age should be a small, irregular assemblage of young stars embedded in a thick blanket of primordial hydrogen gas. What Webb found instead was a galaxy that is unexpectedly luminous, brighter than any model predicted for an object that old. It contains elevated levels of nitrogen, a chemical element that requires the formation and death of massive stars to be produced in significant quantities. The presence of this nitrogen means that at least one full generation of massive stars had already formed, lived, and died before MOMSI-14 was even the age it appears to us now. Stars that should not have had enough time to form yet, let alone complete their entire life cycles. And the galaxy had already cleared the surrounding region of the primordial hydrogen gas that should have been dense around it, which is another process that our models say takes far longer than the time available. The lead researcher's official statement described MOMSI-14 as brighter, more compact and more chemically enriched than astronomers anticipated for such an early era. Another study, Kothor, said the universe appears to have been in a huge hurry to grow up, and MOMSI-14 is not an isolated case. It is one of hundreds. University of Missouri astronomers published a paper in August of 2025 describing 300 unusually bright cosmic objects detected by Webb that defy conventional explanation. 300, not 300 objects, all from the early universe, all behaving in ways that the standard model of galaxy formation cannot account for. Webb is not finding occasional exceptions to the rules. It is finding that the rules themselves may be wrong. But here is where it gets even stranger. Because Webb did not just find things that are too big or too bright, it found something that contradicts one of the most basic assumptions about how young galaxies behave. In May of 2026, a team led by researchers at the University of California, Davis, published a paper in Nature Astronomy describing a massive galaxy that formed less than 2 billion years after the Big Bang. Nothing unusual about that in itself. But when they analyzed its motion, they found something that stopped them completely. This galaxy is not spinning. A massive young galaxy, formed in the early universe, with no rotation at all. Scientists refer to the absence of rotation in a galaxy as a trait seen only in much older, fully evolved systems, galaxies that have been through multiple merger events and whose original angular momentum has been distributed, disrupted, and eventually dissipated over billions of years. A young galaxy should still be spinning because the gas cloud it collapsed from was spinning, and angular momentum is finding a young galaxy with no rotation is, under every current model, impossible. The paper was peer-reviewed, published in one of the most respected journals in astronomy, and it currently has no accepted explanation. At the same time that astronomers were grappling with these impossible galaxies, Webb was producing a separate catalog of objects that were even harder to categorize. In its first images of the deep universe in late 2021 and early 2022, researchers noticed something strange. Scattered among the galaxies and stars were small, very red points of light that did not match any known object type. They were too compact to be galaxies, too luminous to be stars. They appeared during a period when the universe was only a few 100 million years old, and then, roughly a billion years later, they seemed to vanish entirely from the observable universe. Scientists called them little red dots, a temporary name for something that had no permanent name because it had never been seen before. For years, these objects resisted explanation. Then in January of 2026, University of Copenhagen researchers published a paper in Nature identifying what they appeared to be not galaxies, not conventional stars, something the paper describes as young supermassive black holes inside dense cocoons of ionized gas. Objects that formed at the very dawn of the universe, burning so intensely and so briefly that they consumed everything around them, then disappeared, leaving behind the first seeds of the supermassive black holes that now sit at the centers of mature galaxies, including our own, a new category of cosmic object, an entirely new chapter in the story of the early universe, one that nobody predicted and no existing model required. And Webb's surprises are not limited to the distant past. When the telescope turns its instruments toward exoplanets, worlds orbiting other stars, it keeps finding things that planetary science said were not possible. In June of 2025, astronomers announced the discovery of TOI 6894b, a planet roughly the size of Saturn, orbiting a tiny red dwarf star. The problem with this is straightforward. Under current planet formation theory, a red dwarf star does not have enough material in its protoplanetary disk to form a planet anywhere near this size. The gas giant simply should not have been able to accumulate enough mass from that environment to reach its current dimensions. The researchers confirmed it with multiple independent methods of observation. The planet is real. The model that says it cannot exist is also real. Something in the model is wrong. Also, in 2025, Webb turned its instruments on a planet called TOI 561b. This is a world so close to its star that its surface temperature should be somewhere between 4,000 and 4,900 degrees Fahrenheit. Hot enough that any atmosphere of volatile molecules would be stripped away in a geologically short time by the intense radiation environment. The models predict a bare rock at that orbital distance, with nothing between its surface and space. Webb's infrared instruments measured the planet's dayside temperature and found it was 3,200 degrees Fahrenheit, more than 1,700 degrees cooler than a bare rock at that location should be. The only mechanism capable of producing that discrepancy is an atmosphere redistributing heat, an atmosphere that should not be there, around a planet too close to its star to keep one, measured clearly and unambiguously by the most sensitive space telescope ever built. And then there is what Webb has contributed to the mystery of dark matter, the invisible substance that cosmologists believe makes up roughly 27% of the universe's total mass-energy content, the scaffolding on which all visible structure is built. In January of 2026, researchers published the most detailed dark matter map ever created, constructed from Webb data tracking nearly 800,000 galaxies across a region of sky in the constellation, sextants peering 8 to 11 billion years into the past, the map confirms. At its large scales, the theoretical picture of dark matter as a cosmic web of filaments connecting galaxy clusters. But at smaller scales, the map reveals something the standard model does not predict: structures and clumpiness at levels that the model does not account for. Fine-grained features in the distribution of dark matter that are inconsistent with the most widely accepted version of what dark matter is and how it behaves. Some researchers analyzing this data have proposed that the discrepancy might be explained by interactions between dark matter and neutrinos, the ghostly particles that pass through ordinary matter almost entirely unimpeded. That proposal is not yet confirmed. What is confirmed is that the most detailed dark matter map ever made does not perfectly match the most widely accepted model of what dark matter does, and the discrepancy sits at a scale that more data will sharpen rather than resolve. The accumulation of all of this has produced something unusual in a scientific community that is generally careful about making dramatic statements. Researchers are beginning to say publicly that James Webb is not just finding new things within the existing framework. It is straining the framework itself. The standard cosmological model that scientists have built and refined over decades is not broken. It still explains an enormous amount of what we observe, but it is being bent, repeatedly, by findings that sit at its edges and push. One study co-author put it this way, in an official statement published alongside their discovery: there is a growing chasm between theory and observation related to the early universe. A growing chasm, in cosmology, where the goal of decades of work has been to close the gaps between prediction and observation. That phrase represents something significant, not a problem to be solved next year, a fundamental tension between what the universe appears to be doing and what our best current understanding says it should be doing. This matters far beyond the academic question of whether our cosmological models need revision. It matters because every assumption, embedded in how we search for life, for signals, for evidence of other civilizations, rests on a foundation of physics and cosmology that tells us what the universe contains, how it evolved, and what kinds of conditions could support the development of intelligence. If the early universe formed massive structures faster than we thought possible, that changes the timeline for when habitable conditions could have existed elsewhere. If there are entire categories of objects, like the little red dots, that no one predicted, the universe is demonstrating that its capacity to produce unexpected structures is greater than we have given it credit for. And if the dark matter map is telling us that our best model of the universe's invisible scaffolding is incomplete at small scales, we are working with an incomplete picture of the very framework on which all cosmic structure, including all potential life, is built. What James Webb has revealed in 3 years of operation is not a set of discoveries that fit neatly into the existing picture. It is a set of discoveries that collectively suggest the existing picture is missing something, not everything, not the whole story, but something significant enough that the chasm its data has opened between theory and observation is going to require, as scientists are now beginning to quietly admit, not just refinements to the models we have, something genuinely new. And in science, genuinely new frameworks do not arrive quietly. They arrive the same way James Webb's discoveries have been arriving, by showing us something that, according to everything we knew, should not be there.